We study the natural exponential function because it's just a natural function to study. So in this section, we will learn how to evaluate, graph the natural exponential function and use it to calculate continuously compounded interest. So we have this table set up here where we have values of n, and you can see that the values of n are increasing rather rapidly from 1 to a million. And what we're doing is calculating this quantity based on what n is. Now this quantity, as n becomes large, actually the part in the parentheses, 1 plus 1 over n, if n is a large number, actually approaches 1, but is actually always greater than 1, because this 1 over n part is always a positive number, but it keeps getting smaller and smaller as n gets larger and larger. And so this part of this expression goes to 0, and so therefore the complete expression gets closer to 1 as n gets larger. But we have this other n in the exponent, and that makes everything really different. You can see that for various values of n, the calculation of 1 plus 1 over n to the n power appears to get closer and closer and closer to a specific number. You can see how the digits in that decimal number sort of settle down, and here, for instance, at the n equals 1 million, we have 2.718, and then after that a couple of other digits. Well, if you continue to calculate this value, you will find out that eventually the digits begin to stabilize, but always new digits are added on. This is exactly how irrational numbers act. And so what we have is an irrational number that looks like we arrive at this irrational number as n gets larger and larger. The irrational number is the number e, which is a number like pi. It's simply a number that we can't write in the form of a fraction, so it's irrational. And these are the first few digits of the irrational number e. Now, the number e is used as the base for an exponential function. And when the number e is the base of an exponential function, we say we have the natural exponential function. So the natural exponential function is simply the function f of x, which is equal to e to the x. Just remember that e is simply a number, and it's a number that's between 2 and 3. So you can think of this exponential function in terms of that value of e. So for example, since e is between 2 and 3, so we can write this like this, e is between 2 and 3, then we know that e to the x is just some function between 3 to the x and 2 to the x power. So if you looked at the graphs of f of x equals 2 to the x and f of x equals 3 to the x, it would look something like this. Of course, we know that we have an exponential function, and so the x-intercept is 1, 0 for both, so 2 to the x would look like that. 3 to the x, oh, I'm sorry, that's not exponential, that's logarithmic. I'm getting a little ahead of myself here. Exponential function is what I'm drawing. So, okay, so we have... all right, exponential function e to the x. All right, so 2 to the x power looks like this, and 3 to the x power looks very similar to 2 to the x power. It's greater than 2 to the x on the positive numbers, and it's less than 2 to the x on the negative numbers, but they both have the same intercept right here at 0, 1. So e to the x would be between those two. So if I can try to draw this graph, the graph of e to the x would be between the graphs of 2 to the x and 3 to the x, something like that. And that's simply because e is between 2 and 3. So just think of it as a number between 2 and 3, and you probably won't go wrong. You can use a calculator to evaluate values of the function e to the x. On your calculator, there is a key that's labeled ln, and we'll talk more about that key in a later section. But the second function of that key is the e to the x function key. You use this function when you want to use the exponential function e to the x. There's another key on your calculator, the division symbol, and the second function of the division symbol is the number e. So use that if you ever just want to use e as a calculation, e as a number in a calculation. So I'll let you access this function on your calculator to figure out h of 3, h of 0.23, h of 1, and h of negative 2, and just write those all to 3 decimals. Okay, so we can graph the function 3 times e to the x. We can complete this table of values and use it to graph the function 3 times e to the x. I will let you figure out what all those values are that go into this table, and just remember that the graph of 3 times e to the x will be a stretch of the graph of e to the x. So if we look at the graph of e to the x, remember it's an exponential function, so it has a graph something like that. If you multiply times 3, it would seem to make sense that it would be a much steeper, because the y values are 3 times the y values of e to the x, so it would be a much steeper increase there. So what you should do is complete that table of values, use it to graph the function, and then when you're done, look at your TI calculator and graph the functions e to the x and 3e to the x, and see how they compare to each other. Finally, you can use transformations to graph f of x equals the negative of e to the x, because that's just the reflection of the graph across the y-axis. So every x value becomes its opposite. So if this is the graph of f of x equals e to the x, then in the graph of the negative of e to the x, every x value will become its negative. So if you pick a point on the graph of e to the x, which is, say, here, the x value for this function would be the opposite value, which means you have to go across the y-axis to get the x value for the new function, negative of e to the x. Similarly, for this x value, which is a negative value, you want the opposite x value, and so you would go across and go here. So essentially what happens is the graph is just reflected across the y-axis, and it looks just like that. Okay, so in addition to just studying the graphs and looking at the function in that sense, we also have the usefulness of this function in certain kinds of problems. This kind of problem is called logistic growth, and it's just a problem where populations grow, but they're not growing in an unrestricted way because of limited habitat and food supplies. Under such conditions, the population follows a logistic growth model, and this is the model. Notice all those constants in there. We're told what every one of those constants will equal, and they're all positive numbers. So we have C, D, and K. The variable here is T. You see where it says P of T, so T is the variable. Now for a certain fish population in a small pond, D is 1200, K is 11, and C is 0.2. T is measured in years. The fish were introduced into the pond at the time T equal to 0. So if you look at the graph over here, you can see at the time t equals 0, we have a y-intercept right about here on the graph. What we want to know in question A is how many fish were originally put in the pond. Well, the fish were originally put in the pond when t equals 0. And so what we want is P of 0. So let's take a look at that. D, we are told, is 1200. 1 plus k, and we're told that k is 11. E to the negative, well, c is 0.2, so 0.2 times t, which is 0. So here, this part of the expression, the e to the negative 2 times 0, that's just e to the 0, and any number, including e, to the 0 power is 1. So the denominator is 1 plus 11, which is 12, and so this reduces to 1200 divided by 12, and 1200 divided by 12 reduces to, well, I guess it reduces to 100. And so that tells us that 100 fish were originally put into the pond. To find the population after 10, 20, and 30 years, I would suggest that you enter the function into the calculator. So let's see how that would look. We're going to put the function P of t, which is equal to 1200 divided by 1 plus k, which is 11, times, I'm going to put a times sign, e raised to the power, and the power is negative 0.2 times, put another times sign, t. Okay, let me get rid of some of this other stuff over here that we don't need anymore. Get rid of some of that stuff. Now let's see where the grouping symbols have to go. Well, we want to make sure that the calculator uses the correct value for the exponent. And so the first grouping symbol has to go around the exponent right here. We have to make sure the exponent has grouping symbols. Now the calculator is going to do the exponent. It's going to do e to the power negative 0.2t, and then it's going to multiply that times 11. But look over here, it's not going to do the division correctly. We need to make it divide by 1 plus. So notice those nested parentheses to enter this into the calculator, into the y equals, put it maybe in your y1 function that way. And if you do that, then it's really easy to do the b part. You can just look at the table. If you have your table set, if your table is set at ask, table set on your calculator at ask, and auto for the dependent variable, then you should be able to figure out what y of 10, y of 20, and y of 30 would equal. Okay, for the last part of this problem, let's look again at our function in the regular way that we write these things. So we're going to write it up again as 1200. Oh, I've got to get the pen here. 1200 over 1 plus k is 11. And it says e to the negative 0.2 times t. So what I'm going to do is I'm going to rewrite this so that I have a positive exponent, because I want it to be really obvious what's going on here. So 1 plus 11 over e to the 0.2 times t. Get rid of some of these stray marks over here. All right, so now you can see that when the value of t is large, which means t is approaching infinity, it's just a large value of t, you can see that this part of the expression simply goes to 0, because the denominator of that little fraction in there is getting very large, which means that the fraction itself is getting very small. And so what we have here is that this is actually going to approach 1200 as t approaches infinity. Is that what the graph shows? Well, if we look at the graph, we can see that apparently there is a horizontal asymptote at 1200. And that's exactly what horizontal asymptote means. It means as the values of t increase, the function values crowd in on the value of that asymptote, which is 1200. And so the space between the graph and the horizontal line at 1200 gets smaller and smaller and smaller. That space keeps getting smaller and smaller and smaller, which is what we mean by the function values approach. They get close to 1200 as t, the time, increases. We can also use the base E for continuously compounding interest problems. And so we have a formula for that. A of t, the amount of money in an investment after t years, is equal to P, the principal, times E raised to the power R times T, where R is the interest rate and T is the number of years. So again, this is just a matter of entering this function properly into your calculator to figure out that if you have $2,000 invested at an interest rate of 3.5% per year, compounded continuously, this is continuous compounding, you should find the value of the investment after 2, 4, and 12 years. So you just need to enter the formula into the function of your calculator. A of t is equal to P, which is 2,000, times e to the r, which is 3.5% written as a number, that's 0.035 times t. Now again, make sure that when you enter this into your calculator, you put parentheses around that exponent because it's a product, and so you need those parentheses in order to get the calculation done correctly.